The Fourier series states that any periodic function can be expressed as a sum of cosines with different amplitudes and phase shifts. This equation models behavior. X of t is equal to a naught plus the summation from n equals 1 to infinity of a sub n times e to the j 2 pi n t over big T plus the conjugate of a sub n times e to the negative j 2 pi n t over big T. Now I'll explain what all these terms are. A naught is the zeroth harmonic. This is also called the DC component. And this is basically the vertical shift of the signal. So let's say, for example, we had a cosine that goes from positive 1 to negative 1. This would have a 0 vertical shift. But if we had a cosine that went from, let's say, positive 2 to 0, well, we could take this initial cosine, give it a vertical shift of positive 1, and we'd end up with this one. So A naught is just going to be the vertical shift of the initial signal, x of t. And A sub n is going to be the complex exponential coefficient for a given n, which is a number of harmonic. So, for example, let's say we have a cosine that has omega equals 1 radian per second. And all the harmonics are just going to be multiplications of this initial frequency. So I'm going to make a table here. I'll have a column for number of harmonic, and I'll have another column for frequency, and the units will be radians per second. So for the first harmonic, all we need to do is multiply 1 by the initial frequency. It'll just be 1 times 1, which is just going to be 1 radians per second. So it'll just be a 1 in the frequency column. Now for the second harmonic, it'll be 1 times 2, or 2 radians per second. Same thing for 3, it'll be 3 radians per second. And 4 will be 4. Now if instead we started with omega equals 2 radians per second, the first harmonic would have 2 radians per second. The second harmonic would be 2 times 2, or 4 radians per second. The third harmonic would be 2 times 3, or 6 radians per second. So all n is just going to be the number of harmonic, which will change the cosine's frequency that gets summed in the Fourier series. And A sub n will always be in this form. It'll have some magnitude, which will just be a number, times e to the j times phi, where phi is going to be the phase shift of the cosine. And what this whole equation is it's just going to be 2 times the magnitude of A sub n times cosine of omega t plus phi, which is just going to be a cosine with some magnitude and some phase shift. So all this equation is just saying we loop through all the number of harmonics from 1 to infinity, and we sum all the cosines of varying frequencies corresponding to the number harmonic. And these will have different amplitudes based off A sub n, and they'll have different phase shifts also from A sub n. And by summing all these cosines, we can recreate x of t. And all we need to do to recreate x of t is have A naught and have A sub n. So I'll write out the equations for those. The equation for A sub n is going to be 1 over t times the integral over 1 period of the periodic signal of x of t times e to the negative j 2 pi n t over big T, all with respect to time. And A naught will be 1 over t times the integral over 1 period of just x of t dt. Now let's do an example to show how these equations work. So let's say x of t is a square wave. The x-axis will be time in seconds, and the y-axis will be the value of x of t. The square wave will have a minimum x of t value of 0 and a maximum x of t value of positive 1. And it'll have this value of positive 1 from t equals 0 to t equals pi, and it's going to have a 50% duty cycle. So the next square pulse is going to begin at t equals 2 pi seconds. The first step is always to determine what the period of the signal is, and the period is when the signal starts to repeat itself. So as we see, this first square pulse starts at t equals 0, it drops down at t equals pi, and then the next one starts at t equals 2 pi. So the signal repeats itself every 2 pi seconds. So big T is going to be 2 pi seconds. I'm going to write the a sub n equation again. It was 1 over t times the integral over 1 period of x of t times e to the negative j 2 pi n t over big T, all with respect to time. We need to integrate over 1 period, and it can be any period. So for example, we could pick from 0 seconds to 2 pi seconds, or we can pick from 2 pi seconds to 4 pi seconds, or pi seconds to 3 pi seconds. It can be any period of the signal. It's generally easiest to pick ones that give you an easy bound of integration. So in this case, if we pick a period starting with t equals 0, one of our bounds of integration will be 0. So it'll be easiest to pick the period from 0 seconds to 2 pi seconds. I'll write out the integral. A sub n will be 1 over t, and we said t was 2 pi seconds, times the integral over 1 period. We chose from 0 to 2 pi seconds of x of t times e to the negative j 2 pi n t over 2 pi. Now what exactly is x of t in this case? Well, if we look back at the graph, we see that x of t only has two possible values. It either has a value of positive 1 from 0 to pi, or it has a value of 0 from pi to 2 pi. Since there's a portion of the period where x of t has a value of 0, we don't need to account for that portion because 0 times this e term will be 0, and the integral of 0 will just be 0. So the only interval that will actually give us any value for a sub n will be from 0 to pi. And during this interval, x of t has a value of positive 1. So we can write this as 1 over 2 pi times the integral just from 0 to pi, and x of t is always going to be 1 in this region. So it'll just be 1 times e to the negative j, and here we have 2 pi over 2 pi, that'll just become 1, and then times n times t. So the integral is just going to be the integral of e to the negative j n t. And if you remember, whenever you have the integral of e to the at, the answer will be 1 over a times e to the at. So a sub n will be 1 over 2 pi times 1 over negative j times n times e to the negative j n t, bounded between 0 and pi. We can plug in these bounds. We'll have e to the negative j times n times pi minus e to the negative j times n times 0, and e to the 0 is always 1, and that'll all be times what we had before. We can simplify this portion to the left here by multiplying by j over j. On the bottom, we have j times j, which is j squared, which is equal to negative 1. And that negative will cancel with that negative. And a sub n will be j over 2 pi n times e to the negative j n times pi minus 1. Now there's one trick we can do. We can factor out an e to the negative j pi n over 2, and this term will become e to the negative j pi n over 2 minus e to the positive j pi n over 2. And if you multiply this out, you'll see that this term would become e to the negative j pi n, and this term would become 1 again. So this is equivalent to this. I want to keep the coefficient part I had here before. There's a form of Euler's formula that states e to the j theta minus e to the negative j theta is equal to 2j times sine of theta. Now this is close to what we have, except the signs are flipped, where the positive exponent has the negative sign in front, and it should be the other way around. So if we multiply this by -1 on both sides, we get this, where theta is equal to pi n over 2. So what we have in this parenthesis is really negative 2j sine of pi n over 2. So we can substitute that for what we have in these parentheses. And we have this e to the negative j pi n over 2. And this j over 2 pi n. We have a j times a j. That'll become j squared, which again is -1. That'll cancel with this negative sign. We also have this 2 on the numerator and this 2 in the denominator, so those will cancel. A sub n will be 1 over pi n times sine of pi n over 2 times e to the negative j pi n over 2. And a sub n is now in the form that we expect. Earlier, we said that a sub n was the magnitude of a sub n times e to the j phi, where the magnitude of a sub n was the magnitude of the cosine, and phi was the phase shift of the cosine for any given number harmonic. This first part in the a sub n equation we got for this square wave is just a number. So if we plug in an n value, such as n equals 1, we'll have 1 over pi times sine of pi over 2, which is just 1. So it'll be 1 over pi. So the magnitude will be 1 over pi, and the phase shift when n equals 1 will be negative pi over 2. Earlier, we said that the Fourier series was just summing cosines in the form of 2 times the magnitude of a sub n times cosine of omega t plus phi. Since we got the magnitude of a sub n and phi when n equals 1, a sub n, which I'm going to call a sub 1, was 1 over pi, and phi, the phase shift, was negative pi over 2. We can use this equation to plot what that cosine would be. It would be 2 times 1 over pi times cosine, and omega is going to be the frequency. We need to find what that frequency was. The period was 2 pi. The frequency in hertz is 1 over 2 pi. And the frequency in radians per second is 2 pi f. So omega will be 2 pi over 2 pi, which is 1 radians per second. This is called the fundamental frequency, and it's basically the frequency of the signal that you're starting with. So you can think of it like the frequency of x of t here is 1 radian per second. And the harmonics are going to be based off this value. So I'll plug in 1 here for this omega. It'll just be t. And phi was negative pi over 2. So it's t minus pi over 2. A negative value is a right shift, and the amplitude will be 2 over pi, which is about 0.64. So what we'd expect is a cosine with an amplitude 0.64 and a right phase shift pi over 2, which would make it look like a sine. So it would look something like this, where its amplitude would be 0.64. So I'm going to use Python to plot this, and we'll see what it looks like. As you can see, we did get what we expected when we plotted it. This maximum value is around 0.64, and it has the same frequency as the square wave we started with. As you can see, it has a value of 0, and then its positive slope at t equals 0, and then this next occurs at t equals 2 pi. So it has the same frequency and the same period as the square wave. Now there's one more thing we need to calculate before we can move on to using the Fourier series to reconstruct x of t. We need to calculate the 0th harmonic, and you may be wondering why we can't just plug in n equals 0 into this equation. Well, if we did that, we'd have 1 over 0 times some other number, and we can't divide by 0, so that's not allowed. Instead, we have to use the equation that we had for that, which is 1 over t. times the integral over 1 period of x of t dt. And again, t was 2 pi. We can integrate over the same period we used to calculate a sub n, which is from 0 to pi. X of t always had a value of 1, and the integral of 1 is going to be t. So it's going to be t bounded from 0 to pi, which is just going to be pi minus 0. So it's 1 over 2 pi times pi. Those pi's will cancel. So a naught is going to be 1/2. And again, this is just the DC offset of the signal. That a naught value accounts for this square wave effectively being DC biased. If you look, it has a maximum value of 1 and a minimum value of 0, but the cosine goes from some positive value, in this case 0.64 for the first harmonic, down to the negative value of negative 0.64. So signals that have some amount of vertical shift or component in the zeroth harmonic has to be accounted for separately with a naught. If, for example, we get a square wave that went from positive 0.5 to negative 0.5, we wouldn't need a naught and it would just be 0. But for signals that have some amount of its composition in the zeroth harmonic, we need to account for that. So now let's see what happens when we do the second harmonic. In this case, we have sine of pi n over 2, and if n was 2, we would have sine of pi times 2 over 2, or just sine of pi, and sine of pi is 0. So if n was 2, sine would be 0, and a sub n would also be 0. This is true for all of the even harmonics. So let's say n was instead 4. It would be pi times 4 over 2, which is 2 pi, and sine of 2 pi is also 0. So for all of the even harmonics, a sub n is going to be 0. Now this is the case for square waves, and this will change based on the duty cycle of the square wave, and not all signals will have this property, where some harmonics will have 0 for a sub n, but that's just for this case. We don't have to worry about any of the even harmonics. For the third harmonic, I'm not going to calculate it manually. Instead, I'm just going to use Python, and I'm going to plot that again with both the first and the third harmonic. So this is what the first and the third harmonic look like when they're plotted. The first harmonic in blue is what we originally had, and then the third harmonic in orange, as you can see, it has a much higher frequency than the first harmonic, because it's going to be 3 times the frequency. So right now, we're just plotting the first and the third harmonic against each other. But the Fourier series states that when you sum these, you're supposed to get closer to the x of t, which is the square wave. So let's see what happens when we sum the first and the third harmonic. So this is what the plot of the first and the third harmonic summed, including the summing of the zeroth harmonic, which just biased them up 0.5. As you can see, the negative portion of the third harmonic canceled with that positive portion of the first harmonic, and we got this slightly negative shape at the top of where the square wave was. So what this did is it tried to approximate this flat portion of the square wave, and then when the square wave had its value of 0, it also tried to approximate that flat portion. Now we only have 2 harmonics. Let's see what happens when we add a third one and include the fifth harmonic. So this is what the fifth harmonic looks like in green. Again, it has a higher frequency than the other harmonics because it's a higher harmonic. So you multiply 1 times 5, and it's 5 radians per second. And by including more harmonics, we even got closer to this flat portion up here and down here. So when we added more harmonics, we got closer to approximating the shape of the square wave. Now what happens when we include even more harmonics? Let's include the 7th and 9th harmonic and see what shape we get. As you can see, when we went up to the 9th harmonic, we got even closer to approximating this square wave shape. So as we include more and more harmonics, we get even closer to approximating the shape of x of t. So let's try 99 harmonics and see what that gives us. So with 99 harmonics, we've basically fully recreated x of t. And I can even show it by itself without the square wave being plotted against it. And it clearly has that square wave shape. Now you may be wondering what's going on with this part here, and all of the other corners, where it's not exactly the square wave shape that we started with, which would be just a perfect corner. This is what's called the Gibbs phenomenon, and it has to do with discontinuities caused by these infinite positive and infinite negative slopes at the edges of the square waves, which can't be approximated by just summing smooth cosines, since you'd have to have an infinitely high frequency cosine, or you'd have a portion of the slope that was infinitely high, Since we can't actually get an infinitely high frequency cosine, we can only approximate, and we're left with these artifacts. But just by summing cosines together, we were able to get a really good approximation of this square wave that we wanted to replicate, and this can be done with any periodic signal. And you can see my other videos where I found the Fourier series coefficients for different signals, such as a sawtooth wave or a triangle wave. But that's the end of this video, so thank you for watching, and if this video helped you, consider subscribing.